So now we get to start the beginning ideas of calculus with the definition of the derivative, sometimes called Newton's quotient. And there's the definition. F prime of a equals the limit as h goes to 0 of f of a plus h minus f of a over h. Notice this is exactly the same as Formula 2 for what we were doing the other day. So when we were finding the slope of a tangent, and again a little diagram to help us remember, if we wanted to find the slope of the tangent at this green point right there, and we took another point that was close to that green point, the secant line through the green and the blue point would be close to the slope of our tangent, but not quite. And then if we move this point closer and closer and closer, when they're basically on top of each other, and we drew the slope of the secant at that point, it would be the same as the tangent. So this idea of the limit as h goes to 0, and a reminder, when we had that triangle for our slope of our tangent, we labeled this length as h. And as we made that length smaller and smaller and smaller, we got closer and closer to the same as the tangent line. A derivative is just an equation to find the slope of a tangent line. And what the derivative is going to give us is not just one point, because what we did in the other days, we looked at specific points to find the slope. What it's going to find for us is the equation for all points. So f prime of a is that limit, and we write the derivative in this notation. We'll look at some other notations as well. So all the derivative is the slope of a tangent line at any single point in a function. And some neat patterns come out from that. This is Formula 1 from our definition of the derivative. We will mainly be using the other one that we saw before. So this derivative, it is a function, sometimes called a gradient function, because that's another word for slope. And here are a bunch of different notations. So if you have function notation, if you have f of x, you'll often use f prime of x. If you have y equals notation, you can either use y prime or dy dx, change in y over change in x. Here are some of the strategies we're going to use when we're trying to find f prime of x. We're going to use a lot of our algebra skills, because the idea with that limit as h going to 0 is you're dividing by 0. So in order to evaluate a limit, we somehow have to get rid of that h on the bottom. So we're going to plug our function into the definition. We're going to expand, simplify like terms. Sometimes we're going to have to multiply by the conjugate. Eventually, we're going to factor out an h value so we can simplify it. And then we're no longer dividing by 0. And once you're no longer dividing by 0, well, then you can evaluate your limit by plugging in 0 for h. So here's our first example. Using the definition of the derivative, we're going to find f prime of x if f of x is equal to x squared. So here's our definition right here. F prime of x. I've also got this other notation here, dy dx. You wouldn't need to show both of those. Just I'm going to try and introduce the different notations and different questions just so you get used to all of them. So what we do, we're always going to write limit as h goes to 0 until we can actually evaluate that limit. Remember, when you do f of x plus h, you're replacing the x with an x plus h. So in function notation, what does that mean? That means I'm going to have x plus h squared minus f of x, and f of x is just x squared all over h. Just some things to notice. When we're finding whatever variable we're using, when we go back to our original equation, which was right here, here it's f prime of a, then the variable's a. We're using x as our variable, so we have f prime of x. So each of these is just replaced with an x. So it's the same formula, just using a different variable. So here in our equation, we've plugged it into the definition. Now we're going to use our algebra skills to see if we can get rid of that h on the bottom. What's something I can do? I can expand that, okay. X squared plus 2xh plus h squared. Still have minus x squared here, still divided by h. How does expanding help us? Well, this x squared minus that x squared will go away, and we're left with 2xh plus h squared over h. And at this point, we can now factor out an h, because there's a common factor of h in both of those. Which is nice, because that finally cancels out that h at the bottom. Now we can apply the limit, because we're no longer dividing by 0. So when we plug in 0 for h, we get 2x, so that's our derivative. Now part B here, what we were doing before when we were finding our slope of our tangent, we were looking at a specific point. What the derivative does, what we did right here by getting the derivative is equal to 2x, we now have a formula for every single point possible on our original function. So now when we think about what does f prime of 3 equal, what does f prime of 3 mean? Well, now we can take our derivative. We figured out in part A that f prime of any value was equal to 2x. And so f prime of 3 is just plugging 3 in for x. It's going to equal 6. And what does this mean? It means that the slope of the tangent to our function, which was y equals x squared, we can draw a picture of that. Over here, the slope of the tangent when x is equal to 3, which would be at the point 3, 9, the slope of that tangent line is 6. Not 6 factorial, that's just an exclamation mark. It's equal to 6. And what's nice about the definition of the derivative is once we've got f prime of x is equal to 2x, if you wanted to find another one, if you wanted to find, hey, what's the slope at negative 2 comma 4? Well, how am I going to figure out the slope of that line? All I have to do is plug in negative 2 into my derivative. My slope would be negative 4. A key thing that's really important in a parabola is finding the vertex. If you were trying to find the slope of the tangent at that vertex, looking at it, what should the slope of this line be? 0. If you plug 0 in for x, do you get 0? Yes. So what the derivative does is it gives us a formula for every single slope possible. Whereas what we were doing before, we were finding specific ones. Finding it at x equals 3, finding it at x equals 2. So if we do it generally and use the definition, we can find the formula for every single slope possible. And so we can find the slope of any tangent line at any point, no matter where it is on this parabola. And it makes an equation which is just f prime of x equals 2x.